This conference will now be recorded.
Hello, am I audible?
Yes, you are.
A very good morning to all of you who have joined for this session. I am Rehna Bevi, Project Officer, Energy Efficient Building Cell at EMC Kerala. So today we are going to do our webinar series on HVAC design awareness. So I invite Mr. Dinesh Kumar, who is the Head of Energy Conservation in Buildings, Outreach Programs, Standards and Labeling, and Small Hydel Development at Energy Management Center Kerala for the welcome speech.
A very good morning to you all. Myself Dinesh Kumar. It is a wonderful occasion to have in in this particular seminar on awareness on this HVAC design. In fact, if you consider the fact that India having a very long coastal line, the climate being mostly on a hot and humid type of that nature, then with increasing urban population, the necessity for HVAC has been increasing tremendously. If you consider Kerala as an example, we can find that many of the households are slowly getting themselves using conditioned space for their living on a day-to-day basis. That is what is happening. When you have more and more development, as well as when you look for more of a comfortable living for a efficient living and better living standards, people slowly move towards this air conditioning. And I cannot say that India being a country wherein your conditioned spaces, people who are living in a conditioned space is less than 7-8%, and it should not be a very great surprise that people are going with the tide. People are going more and more towards this conditioned space, air conditioned space. In this scenario, HVAC proper design of an HVAC has been we are in a want for a HVAC design in a very big scale. And this and as you all know, the buildings being the major consumers for electricity needs of the country, with all these new addition of air conditioners, it is going to increase on the building and energy demands. Therefore, this today's session on HVAC design will be a very useful session wherein you can understand the intricacies of the designs of that may have to follow. We may have to follow for the HVAC, be it a large scale chiller based thing or a VRF based thing, whichever be, HVAC designs is going to be a very critical factor. And today we have with us Sri Shirish M. Deshpande, renowned ECBC master trainer, who is going to deliver you this technical speech. I would request Rehana to introduce him better in a proper way, but let me welcome Sri Shirish M. Deshpande to deliver his session on HVAC design and awareness. Thank you. From on behalf of Energy Management Center, I welcome Sri Shirish Deshpande. Thank you.
Thank you, sir.
Thank you, sir. So as Dinesh sir said, we have today our ECBC master trainer, Mr. Shirish Deshpande. He has a bachelor's degree in chemical engineering from University of Mumbai. He is a BE certified energy auditor, ECBC master trainer, lead accredited professional. He has industrial and building experience of around 30 years. So we are lucky to have you here, sir. Over to you, sir.
Good morning, all. I would like to share my screen with you and welcome you all for this session where can you see the screen?
Yes, sir.
Just a moment. Yeah. So multiple sessions are there today we are covering. So first we will start with this fuel consumption deviation. Today again we have been talking about crude oil pricing touching about $100 a barrel, which was less than half about a year ago or so due to low demand, and how it is performing. So if you see specifically the rightmost bar of Asia Pacific region, our 50% of consumption comes through coal. Then we have very negligible renewables. Then natural gas and oil are another fossil fuel related energy sources, which overall Asia Pacific has been doing. If you look at this Indian power sector scenario, which is of course a little older, about 4 years old, where 55% of Indian energy this thing also comes from coal-based power plant, then 10% from the gas-based power plant, hydroelectric is 21%, nuclear is about 2%, and renewables are fast catching at about 11%. So gas-based and renewables, which are relatively cleaner fuels, they are known, and hydro 21%. They account for about 40% of generation, and slowly there are targets that we would try and reduce our coal-based thermal power plant emissions to 0 by 2050 or so. And so we can't have much more of hydro now. Renewable, there is a tremendous scope, and gas also will have a limit because end of life of these fossil fuel is expected to be another next 20 or 30 years, and coal might survive little longer than that. If you look at sector-wise energy consumption, then your agriculture is one of the major source of or area of consumption. Residential is fast catching, and commercial buildings which were not existing maybe about 15 years ago or so have also significant consumption among the other sectors. Then again, in the commercial sectors, we have offices which are 21%, hospitals which are about 18%, hotels which are about 38%, or sorry, hotel are 21% and offices are 37%. And if you look back probably a couple of decades ago, most of these hospital, offices and hotels were not air conditioned, or there were not definitely centrally air conditioned things. So as probably lifestyle of people have changed over period, and there could be many factors, but and computerization also added to need of air conditioning to be in office. So all those factors have gradually increased our energy consumption demand. So if you look at a standard non-air conditioned office building, which was typically a government building couple of decades back, used to consume about 20 kWh per meter square per annum in terms of EPI. And the glass box buildings, which are built all over the country, are typically consuming about 250 to 350 kWh per meter square per annum. So this 10 times increase in consumption is mainly on account of building envelope, which has changed from traditional structure to a glass box envelope, as well as load of air conditioning, which has gone up significantly, and related activities. So even educational institutes nowadays, they need air conditioning. So in one way, we are probably saying yes, we need to conserve energy, but then we are saying okay, we want thermal comfort. So while working, while studying, while eating out, yes, we want comfortable condition. Climate in all coastal areas across India, all east coast, west coast, both, we have very high humidity traditionally and higher temperatures. So we talk about temperature range of more than 33 degrees centigrade to about 39 degrees centigrade across Calcutta to Mumbai, or parts of Gujarat. And we talk about more than 70% humidity as a whole. So except for some hilly areas of Kerala, entire Kerala as a whole comes into a warm and humid climate, which is predominantly high temperature and high relative humidity. So where we perspire, we sweat. Similarly, where I come from, Mumbai is also similar place where we have practically negligible or no winter, but always ceiling fans or something are required to keep us comfortable. So when we talk about thermal comfort requirement and air conditioning, they go hand in hand for most of us, because for the whole year we would be depending on them to keep us comfortable. So with this background, we need to look at an integrated design approach as a thought process. It's been noted that it follows a certain set of guideline or requirement, which will eventually say, yes, we need to meet owner's needs. Demands may be anything, but at least needs in a sustainable manner without compromising a requirement. So we need to discuss, we need to understand their needs, we need to apply our design technique. Again, we need to analyze, evaluate, and if nothing works out well, then you go back. So for all this, we need to analyze and evaluate, we need a reference standard. And all that reference standard provide us a guideline, yes, whether we are doing fair or not. Like an example of say our standard blood sample report, we take it from a pathology lab or something. They will talk about hemoglobin, they will talk about compact cell, they will talk about so many things. But on the right hand side, there would be our value and a reference standard. And then looking at reference standard, even we don't know anything about medicine or pathology, we can deduce yes, whether we are good or bad. or for certain things like hemoglobin, yes, we can understand whether it is more or less or something. So that reference on the right hand side column provides us a good probably initial indication how we are doing. So when we want to construct a building, either residential or commercial, we need to have some reference standard. So when energy consumption was less, there were no reference standards required as well. You will put a ceiling fan, you will put a bulb or a tube light, and that's fine. You will be comfortable, or because the bills were not this thing. But the moment you install one air conditioning of say 1 ton, your energy consumption and use it even during only night hours at home, your energy bill will go up by 1500 to 2000 rupees a month. If you put multiple of them, it will have a same multiplication factor. So rest of the systems, energy consumption could be about say 500, 600 or less than 1000 rupees. But if you introduce just one air conditioner for comfort, then it would start eating into place. Fortunately, India long back graduated from use of bulbs, which produce heat, more heat, 80% heat, and just 20% of light comes incidentally out of them, to a cool fluorescent lamps long back. So in terms of lighting energy efficiency, we were always good. And now over the years, we also quickly shifted to CFL and also to LED. So now in every household, we understand and we know, yes, we have LED lamps. But what about our ceiling fans? What about our air conditioners? They still consume to or add to more consumption level. So if we are talking about design approach, then yardstick is required, and that was the this thing main basis where Bureau of Energy Efficiency was formed under Energy Conservation Act 2001 in Indian Parliament, and it is being implemented. It is always said that optimizing components in isolation tend to be pessimistic, and hence entire bottom line of the system. One can actually make a system less efficient simply by not linking up these components. And if these systems are not designed to work with each other, they will tend to work against each other. I'll give an example. If we want or design a home or an office to have 100% natural lighting, and we try and eliminate use of artificial lighting during the day whole time, then naturally we will have to keep more windows, more openings, and then for those openings we will install either glasses, which would also, or but if we won't provide a chhaja or a shading, then a lot of heat also will come along with that, and the whole place will not be easy to sit or work and make us thermally discomfortable. So in order to avoid use of artificial lighting, we invited another trouble of inviting heat inside the building. So, but on the other hand, if we say, yes, I want my building to be thermally comfortable, like older houses or caves, which have predominantly thick walls or something, then our cost of construction would go up. And also, if we keep smaller windows, then most of the offices or homes will have to live with artificial lighting through the day, which will also increase cost. So we can always have some optimum numbers in every aspect of a construction. That could be envelope, that is wall, windows and roof, which need to have certain design aspects. Then we can shift to the internal loads. Like earlier, we used to have CRT monitors on the huge desktop computers, which used to consume about 250 watts. Now our slick LED or LCD screens, they consume less than 100 watt, and laptop monitors are consuming just about 65 to 70 watts. So this progression, but then all this we talk about watts. But when we talk about just 1 ton of air conditioning, we talk about 1.5 kilowatt per ton of capacity, which is huge. So that's why we need to make this building efficient and also use this or some yardsticks for making. So if a energy consumption of a building process is analyzed, so 100% is a business as usual case. Then what we do, we look at passive measures where we consider orientation, window to wall ratio, glazing, shading, insulation, natural ventilation, daylight, all these passive aspects of design, and try and optimize our energy consumption by these measures. So which will minimize heat gain and would maximize daylight to an optimum level. Then we would introduce active measures like pre-cooling, energy recovery wheel, evaporative cooling, chiller selection and operation, innovative technologies, etc., which will have efficient air conditioning and lighting system and other controls. And thirdly, we will introduce renewable energy on site. Mostly it would be solar hot water system or solar photovoltaic system, and maybe in some coastal sites or something or highland sites where there is a predominant wind available, maybe some captive or campus level windmills can also be looked at. And then balance of system, you will take it from the grid. So in that manner, if you can see, we have been able to achieve significant amount of energy consumption, which could be to the tune of about 25 to 40% if we design all these things in proper. But the sequence is more essential. You can't start with installing a solar system unless you have put some active measures controls as well as have done your design using passive measures where your orientation, shading, insulation, natural ventilation or cross ventilation, daylighting is taken care. Because otherwise you would be putting all your energy usage into a leaking pot where through a uninsulated building envelope you will lose cooling, you will install inefficient system which will consume more energy. If you look, remember now we talk about BEE certified 3-star, 4-star, 5-star ceiling fans. Not long ago or even today in some rural markets, some unbranded ceiling fans are available. So we have a BEE star level rating program for ceiling fans. So where they guarantee that this ceiling fan will consume about 40 watt or maybe even 35 watts of power for a 5-star rating. And if you go with brushless DC or BLDC fan, it would consume less than 30 watt of power. But then that fan could be available say at 2000 rupees. And in the local market with at your neighborhood hardware store, if you ask for a cheaper fan, he will give you some unbranded fan, and which could cost say about 1000 rupees, 1200 rupees, almost half or 60% of the star label fan. But when you will end up, but then it will keep on consuming minimum 90 to 100 watts of power as compared to 30 watts. So that cost of saving probably, and the once you install that ceiling fan, it would continue to be there in your house for next 10, 15, 20 years, you don't know how many years. And then that additional incremental energy consumption between 100 watt and 30 watt, that differential you will keep on paying in your monthly bill, and probably you will end up losing more of 600 rupees per multiple ceiling fans in a month itself. So we need to look at all these options. So when we want to use active systems, when we want to talk about adding rooftop solar, in Kerala you have many independent houses in major part of the state, not maybe in city like Trivandrum or this thing, but as a whole. So people tend to have solar PV and people tend to have maybe a solar hot water system as well. But the type of construction we are doing is the same which was there when we had unconditioned houses. So we allow a lot of heat to be gained by our structure in a traditional manner, and for not losing air conditioning we shut our windows, so there is no cross ventilation, there is no fresh air coming inside the building. At the same time, our envelope which continues to be like 150 mm thick RCC slab and maybe 100 or 150 brickbat coba about it, just to so that the water doesn't percolate through the slab but get a slope. And that U value or thermal heat gain coefficient of that structure is much higher than something. So traditionally you will wear a cap or something if you want to go out in the sun, or even want to protect yourself in the rain, you will carry an umbrella. But if you want to consume energy for your household, we don't change our construction techniques and methodology of doing that. We still construct our houses in the same manner which were using for unconditioned home, where only ceiling fan and cross ventilation was good enough. So when we need to look at integrated design in the entire process, when we start with the conceptual design, schematic design, design development, then generate construction drawings, and during the construction process, commissioning and handover. So the earlier, all people like client, architect, HVAC engineer, structural engineer, maybe green building or energy consultant, they start working together. This is the place where they need to start at just around conceptual design and before schematic design is in place. Earlier we will have less efforts to put, as well as our cost also will be controlled. If you already release a tender or appoint a contractor to construct a building, and then you start thinking about adding energy efficiency into the system, then we are nowhere, because then at that point of time, cost of redoing few things or adding some components will be always higher, and it would automatically escalate your budget. Green buildings, when I work as a green building professional, many a times I encounter one question from the clients is that always green buildings are going to be costly by 15, 20, 30%. My answer is no. Yes, if you want to have, say, GRIA 5-star rated, or if you want to have LEED or IGBC platinum rating, you may spend 5 to 7% extra. But to make a building gold, silver, or just certified level, or even GRIA 3-star or below, you would actually consume less energy or less cost as well. First cost I'm talking about. But if you start it at conceptual design or schematic design stage of the project, so you start with that. But if you say, yes, I will construct a building as usual, I will create a glass box, allow a lot of heat to come inside because I want 100% glazed building, which is not required in our climate. And then if we want to put additional or super efficient chillers, air conditioning systems or something, yes, then we will end up having more consumption, because or spend more money as well to buy a higher capacity chiller. See, this is something I can show you, or it's one of the case studies we will take again in this thing. But just one slide I want to show you here is, before all these discussions about energy efficiency, this particular building had a cooling requirement of about 225 tons with a standard design. Nothing right or nothing wrong about it. But when this discussions of integrated design and design chariot and if ECBC label building happened, the cooling came down to about 165 TR. So about 28% reduction in cooling system sizing itself by doing better envelope. So this is an impact of doing a better envelope design, where you have good amount of window to wall ratio, as well as adequate openings, orientation of building managed, and roof insulation, adding high reflective paints for the roof, etc. You will reduce your need for air conditioning inside the building. And this is where you will save your first cost. If you take as a thumb rule about 70,000, 75,000 rupees per ton, both high side, low side, and ancillary systems put together, so this 28% reduction, say 225 ton cooling versus 165 ton cooling. So that component of about 60 tons of saving. So 60 tons into 75,000 rupees was the reduction in first cost. And then that probably wholesome or even part of that would go in improving your building roof or building wall properties or materials. So additional cost you will spend for making your envelope better will actually help you in the other way. And when we discuss about case studies in the final session, we will discuss about all these aspects. But this is where we are saying, yes, by doing right things, we will have a much better system to operate, as well as our cost of operations also will come down in terms of monthly bill. So the key learnings of these kind of designs in last so many years are: reduce your demand first through passive measures, then use efficient system with controls, and then integrate renewable energy system. You won't buy a two-wheeler or four-wheeler without any gear. Even in auto mode of Activa or any other scooters or even cars, there is a gear which automatically shifts. But if you just put your car in one gear and just try and operate it, it would turn out to be highly inefficient. In the first or second gear, it will try and deliver you more torque and less speed. So because most of the energy will give going into the torque generation at a gear ratio of first and second. But when your car has overcome the initial inertia, it would need a speed to maintain. And also we need brakes to break that speed or something. So controls in terms of gears as well as brakes are required so that we operate efficiently. So similar way in a building, where even if you design your chiller for a very high COP of more than 6.5, 6.7, which you will buy in the market at a higher cost. But if you don't put low side controls or the pumping power controls, variable frequency drives or something, you will end up consuming more power because it will keep on providing you cooling at its rated capacity irrespective of your needs. So it would not modulate as per your requirement. In the monsoon or in the peak of summer, there will be high humidity, so you will have to lower your chilled water supply temperature to get rid of that extra humidity. But even in mildest winter of say December or January, even in Kerala or other coastal parts of India, where relative humidity is lower, you can slightly increase your chilled water supply temperature to about 8 degrees or 8.5 degrees and save significant amount of power on chiller consumption. Because in entire air conditioning system, 40 to 50% contribution is of chiller only, and then pumps, cooling towers, and air handling unit consume balance of load. Through the day, we will discuss about these aspects. But when we say yes, if I buy just efficient chiller but don't put any controls on the balance of system, my chiller will still be turn out to be inefficient when I will compare a system with controls. And how to do that? There are yardsticks. And that is where ECBC or Energy Conservation Building Code was introduced way back in 2007 as a first this thing. And based on those buildings which were constructed, then Bureau of Energy Efficiency evaluated performance of more than such 300 or 400 buildings across India, across all 5 climatic zones. And then they come out with the next version of ECBC 2017. And then they created 3 levels of buildings: ECBC compliant, ECBC plus, and super ECBC buildings. So each subsequent higher efficiency will be at least 15 to 20% more efficient than the previous one. And maybe as per the plans what we have or the BEE has declared is that in next 5 or 7 years, maybe ECBC will get scrapped. ECBC plus, existing ECBC plus will become then ECBC. Super ECBC will be downgraded to ECBC plus, and new level of efficiency as a super ECBC will get introduced. And then this cycle will keep on churning, like those of you who are conversant with the designated consumers, which are designated by Bureau of Energy Efficiency under patch cycle, performance analyze and trade. So under patch cycle, these designated consumers, they get energy performance targets like cement, then your fertilizers, then steel. All these segment, they get their annual targets from BW, and successfully 2 such patch cycles have already been completed in industry. Building is another area which is also among the 20 designated consumers. So buildings will also have the ECBC, and this is where the ECBC cell sitting in the every state nodal agency, like here in Kerala Energy Management Center, they will govern all these developments and the capacity building. So what we are discussing today is a capacity building and understanding the entire whole process of how this will work. So then all these ECBC compliances through the local municipal councils or this thing, they will govern. If you are talking about constructing a bigger project or building and involving many players or designers like architects, civil engineers, HVAC, electrical engineers, etc., mechanical plumbing engineer, then you will have a battery of knowledgeable people. But if you want to construct a small office building or even a house, you won't probably have all these consultants directly or indirectly working on the project. So that is where the prescriptive approach comes into picture. So what is prescriptive approach? If you're not feeling well, we go to our doctor, then he writes a prescription, which only probably our chemist can read. He gives us that medicine, we take that medicine faithfully, and probably we get cured most of the time. So that's a prescriptive approach. We don't understand what is there in those tablets or injections or capsules, but we take that prescription, have those medicines as prescribed by the doctor, and we get well. The prescriptive approach of ECBC is always also in the same manner. They say, okay, you do these things or use these materials, you will automatically be ECBC compliant. They don't ask you to scratch your head to calculate a U value of whether you need a walls of U value of 0.44 watt per meter square hour degree centigrade. If we don't know, we don't know. But then if we know what material to be used, they will prescribe you to use, say, 230 brick with say 1 inch of insulation, or you use combination of 115 of hollow concrete block plus 2 inches of EPS or XPS insulation and AAC block, you will still achieve that U value which is required for ECBC. And then these are materials which are available in the market. Same way on the roof, brick bat coba, they will say, yes, use 2 inches of insulation of EPS or XPS, you will be done. Or you do an underdeck insulation for the topmost floor, your roof is governed. And then you will achieve a U value of 0.216 watt per meter square degree centigrade. Provide shading of 600 on all your windows will be good enough. And then they say, your window to wall ratio should not be more than 60% in a prescriptive method. So all such simple measures allow us to construct still a efficient building or energy efficient building by using prescriptive. But if you, for a larger project, if you have battery of consultants available and educated design team, then they can do energy simulation, they can also evaluate multiple options and then come out with a solution what to do or not. So when you try and look at impact of everything, there is a method called energy simulation where you can simulate the building before it is constructed for its predicted usage. So you create two cases. One is a base case or a design case, which would go with the ECBC prescribed values and have annual energy consumption generated. And then you construct your or compare that case with your design case. and then look at under which heading or component you are losing or consuming more energy than base case, and try and put some solutions even before at the design stage itself, before even you write any standards or release any tender document, and then meet those values and achieve energy efficiency. So both these finally roads will help you in attaining your goal of energy efficient building design as well as construction, and ECBC helps you. But this happens, ECBC was made for commercial buildings. Of initial was about 600 kV or 500 kilowatt of connected load, but later it was also found out, so somewhere in 2010-11 it was amended, and any building of consuming or having connected load of 100 kW or 120 kVA will be coming under purview of ECBC. See, because building once constructed will last for next 30, 40, 50 years, and then if it is constructed inefficiently, then it will keep on consuming more energy through its life cycle, and that would be more deterrent. So India is talking about attaining net zero buildings by 2030 to a 60%, and maybe in subsequent 10 to 15 years, all our existing building stocks would be net zero. So upgradation of existing building as well as constructing new buildings will keep on happening. And even government predictions, Niti Aayog is also saying that about 4 times more buildings would get constructed than today's building stock in next 20 or 30 years. So it becomes very important that buildings will keep on consuming less and less energy, and they are designed appropriately. See, typically we have seen, like I had mentioned, this so-called new buildings or glass box building, they keep on consuming about, in climates, coastal climates. I'm still not talking about building constructed in Gurgaon or Delhi or North, because they consume much more energy in summers, but save something on winters as well, when they have very harsh winters. So no air conditioning is practically required. But then these buildings consume about 250 to 350 kWh per meter square per annum. And then energy performance index, it has to be between 70 to 100 kWh per meter square per annum to achieve BEE 5-star rating for the buildings. To reduce that energy consumption by more than half is the first goal of the entire exercise, and then you try and work out how you will save further. So you add up controls, then you add renewable energy generation and do it. So probable target would be somewhere around in next another couple of years, or maybe in next 10 years, to construct a building which will have energy consumption of about 65 to 85 kWh per meter square per annum, air conditioned building we are talking about, or thermal comfort, and then you generate that energy required, majority of them through the building integrated photovoltaic or building integrated wind turbines or something, and try to be carbon neutral or energy self-sufficient. So that's the overall target or a way. In this manner, these guidelines would be working and get improved. Even in ECBC 2017, government has also emphasized on having, or they have recognized 8 alternate cooling technologies. So alternate cooling technologies is what? Something like in entire central and northern India, desert coolers were always used during the summer months, where they have very low humidity. So by adding water in front of a fan and then throwing that humid and cool air in the household was one easy and less energy consuming measure or way of having a thermal comfort. But of course, that humidity becomes uncontrollable and it will have its own side effects, but still your energy consumption or air conditioning load would come down. So direct and indirect evaporative cooling. Then another way is adding a radiant cooling system or structural cooling system, or allowing mixed mode use buildings. So whenever your climate is good, you will have openings or openable windows, doors, anything which will allow directly cool air to be taken inside. So entire composite and hot and dry climate of northern India can enjoy these kind of cooling system, where during winter they won't need this building at all, air conditioning at all in those buildings, and just a ventilation fans, pressure dissipation system, and lighting load would be there. So EPI of those building would be much less than 65 kWh per meter square per annum, both summer and winter put together. So all these alternate cooling techniques are also recognized now in ECBC, and if you are meeting 30% of your total cooling demand by these alternate cooling technologies, then your ECBC compliant building can be called as ECBC plus building, or your overall ECBC plus building can then also be called as a ECBC super ECBC building. So integrated design approach in the early stage will help us in 20 to 40% energy saving, and share it or design meets prior to you actually put anything on physical site at the design stage itself. If you can analyze techno-economics of these, then it can have a easy way to achieve your energy conservation. Yeah, there was some in the chat box. In Kerala, what would be the potential of solar cooling through vapor absorption route of air conditioning sourced from solar thermal energy? How good is Kerala climate condition to suit technology for implementation in office and commercial buildings? Yes, so answer to Mr. Anish Rajendra's question, I would say probably my experience of doing solar air conditioning through vapor absorption machines in Mumbai. We have done this project about 10 years back of 165 tons of solar air conditioning through using VAMs. But our experience is by end of April or early May in Mumbai, or maybe it will be 1 month prior to that in Kerala, because monsoon reaches your place little earlier than us. When climate becomes cloudy, your solar thermal system stops or reduces the output of steam significantly. So then you don't get enough cooling, and practically in 4 or 5 months of monsoon, there is hardly any generation of this thing. And when you receive more than 3000 mm of rainfall in Kerala, and some when monsoon lasts for almost like 4 months, and you have cloudy overcast skies for more than 70% of the year, I would not say from my own experience that it would be a very wise uh, thing to go for a large scale cooling. But maybe for school, colleges, or small health centers, or remote office, this thing, healthcare centers or hospitals at rural stage, yes, it can be used and coupled. But instead of generating steam, if you can use evacuated tubes to generate solar hot water through a solar system, and use that solar, sorry, hot water based VAM, which will have a low COP, but at least through evacuated tubes we can generate hot water even on a cloudy day, and then use that. So when you are having solar energy available free or heat available free, and capture that to generate hot water, and then use some additional amount of energy source like heating that water to getting it pressurized to 110 degree or so, you will have a good chance of installing them. But for large commercial complexes in the high-rise buildings in the bigger cities like Ernakulam or Trivandrum, probably I won't say it would be a very good idea, because we did this in a hospital, municipal hospital, and it was a horizontal 4-story building with very large roof area. So we could accommodate all our solar panels there very easily and balance of system. In commercial building, if it is a vertical high-rise building, then you may not even have enough solar area. And if you go with a big solar dish of 150 meter square or something, then your building has to be structurally designed for that. So then retrofitting that may not be very economical in the beginning. So solar thermal VAM operation, if you use it with hot water generation system, then that's good. But even in Mumbai also, this hospital, we have put a agro residue fired briquette boiler as a backup fuel, this thing. So in last 13 years or 14 years, that hospital has never used their old electrical chiller, that I can say. So all their night requirements and monsoon requirement, they operate this boiler, which operates this consumes agro residue briquette. It was in fact a CDM project back then, where we have eliminated use of fossil fuel based energy generation coming from grid, and entire air conditioning is made through VAM throughout the year, but either partially from solar and partially from the agro residue briquette boiler. So all these combinations have helped them to operate without using electrical chillers for last 13-14 years. So that I can say, yes, that system works, but then it cannot be generalized, is my view. So now we will come back to ECBC again, but then larger amount of residential buildings are also built across the country. And now there is already a debate happening between the available land space, which should be used for buildings or residential buildings, or it should be dedicated for the food security, that is for agriculture. So over years, lot of agriculture land has gone to industrial development as well as residential building, which is happening. So we don't have much of, probably we will have more population and less of space under agriculture. Even in Kerala, you have a lot of cultivation. So there is a greenery, but that majority of that cultivation has gone into cash crops like rubber or cashew or something, which may or may not be this thing giving or sustainable to the overall ecology of system. We will not go into those details, but then if you have one type of crop cultivation, it adds to a lot of other areas. It can be a good example of Punjab and Haryana in North India, where they produce basmati rice, which is a cash crop for them. And as we all know, for rice, you need a lot of rains and water to be in the paddy fields so that their roots can then absorb that water slowly and rice is grown. And in the northern part of country, the water table has gone down because of excessive drawing of this groundwater. And now those farmers, they are not willing to change the crop type because other crops will not give them the same amount of revenue. And this is not new. This has happened in California, where they have a lobby of orange growers as well as almond growers. So almond lobby in California is also similarly dominant and have been asking for more and more water. And the groundwater table in those areas have gone below several hundred feet. So it's not just one problem here in India, it's globally it is happening. So when you have this kind of conflict of available land for residential or industrial development, then you have these issues. And one such area is residential building, which will come in every nook and corner of the country, not just in big cities or something. So even constructing residential buildings as per the energy efficiency guidelines, this Eco-Niwas Samhita was conceptualized and made available for public usage. And the part 1 of ENS or Eco-Niwas Samhita was only dedicated for envelope design. So you design your residential building envelope in a most energy efficient manner and run, and then you have this thing. But in 2021, The second part of Econivas Samhita was come into picture, which also accounts for electromechanical and renewable energy systems, or ENSCN2, which is a code compliance for residential buildings built on a plot area of this thing greater than or equal to 500 meter square, and residential or part of mixed land use projects built more. See, the code is also applicable for all additions made to the existing residential buildings where again building area exceed the minimum requirement of 500 meter square of plot area and construction. So demonstration of energy compliance for residential building is also on radar at all levels, right from central government policies to the state government policies, and there are ways and do. So like ECBC, where you take care of your envelope design or passive measures, then you put controls on your electrical systems, metering, submetering, cable, transformer efficiencies. Then you talk about air conditioning system, that is chiller COP or efficiency. Then you talk about pump efficiency, motor efficiencies, controls, additional controls, and you talk also about renewable energy generation and have an EPI which is compared to be target. Similarly, in the residential buildings, again, all these criteria like service hot water, renewable energy, envelope design, air conditioning usage for providing thermal comfort is also of critical this thing importance and nature and need to be addressed to. See, one thing about all these codes all over the world, even if you take ASHRAE 90.1, which has been upgraded so many times in last 30-40 years, or even our ECBC, which has been there for almost like 13-14 years now in the country, these are minimum efficiency codes. That means it is not that we achieve minimum value prescribed in ECBC, then we are efficient. No, we are then if we achieve same efficiency of ECBC compliant building, that means we are just meeting the code, and there is always chance of improving this performance by 10, 15, 20% very easily, and then we are better than that. So all over the world, all these codes, they are probably account for top 60 or 70% of the lot of buildings respectively for their own climates and their energy consumption. So achieving ECBC compliance is not a great design. Yes, it has to be there. Earlier there was no yardstick. Now we have a yardstick of ECBC. And similarly for residential building, ENS or Econivas Samhita. But we can always beat, and they are aimed to be beaten. And that is how, as I mentioned, in next 5-6 years, probably our current lot of ECBC standards would go down or out of system, and then ECBC plus will become new ECBC, super ECBC will become new ECBC plus, and new super ECBC will be introduced. Like in vehicles, we had BS1, BS2, BS4, and now BS6 of rating or emissions for the vehicles. Similarly, we have something for buildings and residential and commercial buildings as ECBC and ENS. So ENS again gives you an opportunity for all the buildings which are significant, so they need to ENS2, right, which is called ENSCN2 provision. They call for minimum requirements of electromechanical services in the building, that is for common area, exterior lighting, basement ventilation, use of transformer, power distribution, etc. And then also indoor lighting or indoor comfort system, which could be ceiling fan and air conditioners, as well as service hot water. So ENSCN2 sets minimum requirement of energy. Just a second. So if your building project has more than one building block in multiple orientations, then the compliance must be sought by showing that building block meet the performance of requirements in each of 4 cardinal orientation, that is north, south, east, west. But if you have identical building blocks in the same orientation, like buildings which are one behind the other in the same exact same direction and almost similar geometry, then compliance only to one block can be sufficient. And any policy notified by taking precedence over these codes can be as per the safety, security, health, and environmental policies of state and central government. And then BEE standards and labeling for appliances and other applications will, and the future improvements in those standards will also be taken care as a standard measure. So if ECBC star labeling, which has also gone up, so for appliances like refrigerators or televisions or even other equipments, even lighting, ECBC star labeling has undergone 2 or 3 cycles of upgradation. So what was earlier previously 1 star that goes out, or previously 2 star that goes out, and new level of efficiency comes into. So your window and split AC units, refrigerators, which consume more energy, they are probably the available AC units now available in the market need to meet those requirements. So that's the beauty of star labeling. Then the compliance approach here is also very similar to ECBC. That is, we have prescriptive approach, which has been mentioned in chapter 5 of ENSC2 code, and point-based system approach, again as mentioned in chapter 6, where low-rise buildings will have to have minimum ENS score of 47. Affordable housing will have minimum score of 70, and high-rise building will have minimum score of 100. So how these buildings or categories will be defined under low-rise or affordable housing or high-rise building. So building equal to or below 4 stories and or building up to 15 meter in height, that is without stilt, or 17.5 meter in height including stilt, will be called low-rise building. Affordable housing projects would be dwelling units of carpet area less than 60 square meter or 600 square feet, and it will also include economically weaker section category and lower income group LIG category. So LIG A, which will be between 28 to 40 meter square or 280 to 400 square feet of area, and LIGB will be 41 to 60 meter square area, which will be 410 and 600 square feet of area, which has been mentioned in chapter 7 of ENS. And a high-rise building which is more than 4 stories, exceeding 15 meter in height without stilt, or 17.5 meter in height including stilt. So all buildings above 5 floors and more will be called high rise for the calculation of ENS criteria. Because more than 4 floors, again requirement of elevators come into picture in as per the local bylaws in most of the country. And also there is a compliance requirement for mixed mode of buildings, where again we have lower floors or ground floor we have commercial shops or offices, and above that we have residential areas. So all these mixed mode use buildings also will be in the compliance approach of ENS CN2. If the part of the mixed use building classification, either residential or commercial, is less than 10% of the total above grade floor area, the mixed use building part shall show compliance based on the building sub classification. So that means if more than 90% of your flats are residential and only 5%, that is less than 10% of the total built up area are only for shops, then it will go only as a residential building. But vice versa, if you have only 2 floors of residential and 6 floors of say commercial, for example, it could be like rented apartments or suites or something where long-term lease apartments are there on the top of commercial building, then they will follow guidelines of commercial buildings as well. Basement and common area services designed for these buildings will also have compliances of local authority as well as ventilation and other requirements as per the safety and statutory. In a mixed mode building with different category of residential buildings in the same project, including one or more categories as listed in 3.1.2 of the ENS code, which is for low rise and affordable housing and for a high rise building. The compliance for site marked for affordable housing should be as per the applicable bylaw and need to be shown separately. Then overall point to be achieved in ENS building for site mark for affordable housing is 70. That means in many parts of the country or bigger towns, there is a complex residential complex which comes up, which contains both affordable housing as well as high-end residences. So then if we dedicate or the earmark those buildings or part of those buildings, then as that part, whatever is applicable by law should be then consumed or measured by those numbers. So for low rise building, overall point score is about 47. If the site area with low rise building in our project is less than 20% of the total site area, then the site mark for low rise building as per the applicable bylaws shall be shown together, and overall point score for ENS compliance for the overall site is then 100. That becomes the benchmark line. So just a second. So when we talk about compliance approach, there are mandatory points. So the compliance to be shown only for the components which are provided in the project and is necessary as per the applicable bidding bylaws. And then the additional points are to claim additional points of any component in the building services and indoor area services mentioned in 6.5 and 6.6 section, except for the requirement for basement lighting. Project need to install a component for minimum 80% of total above grade area or component design for 80% of total aggregate above grade area. And to claim additional points for requirements of basement lighting mentioned in section 6.5, ENS building to show compliance for total basement area designed in the project and as per the applicable building bylaw. And to claim these additional points, building also need to install additional requirements of system. And then if we are talking about point system method, in order to demonstrate compliance with the code through point system method, the ANS building shall meet all applicable mandatory requirements specified in chapter 4 and obtain minimum ENS score as per section 6.1 of chapter. And so all low-rise buildings must obtain a score of 47. All affordable housing scheme must obtain score of 70, and all high-rise building must obtain minimum score of 100 points for building envelope and building services, and indoor electric end use and renewable energy systems under section 6.4, 6.5, 6.6 and 6.7 respectively. And then prescriptive approach. In order to demonstrate compliance with the code through prescriptive method, again I said yes, you meet these mandatory requirements mentioned in chapter 4 and all in chapter 5 for the compliance purpose. So this is the table 2 of ENS building for each category. So building envelope, you need to score 47 points. You can get also additional points 40 for envelope, and then maximum points allowable are 87. Then for building services, that is common area and exterior lighting, you have minimum 3 points, maximum 9 points with additional of 6 points. Elevator, there are a minimum 13 points. That is the regenerative braking is mandatory part of that of elevator system installed. Then additional points of 9 you can get for using VVF controls, etc. So elevators will become 22 points. Then pumps, you will have 6 point mandatory and additional points of 8 are available. Then well, electrical system for efficiency of transformer, cable, APFC maintenance, you have 1 point. And as you add these other submetering and other areas, you will get additional 5 points. Then for household or indoor level electrical end use, you will have indoor lighting and comfort systems. So comfort system will have additional points of 50, and indoor lighting you will have additional points of 12 lighting this thing. So again, ENS score can have some, minimum 70 and additional points of 130, so that becomes 2. For additional points, the code will also provide additional points for renewable energy as mentioned in table 3. So this is a table 3 which I have reproduced here. So under section 6.7 of ENS CN2, renewable energy system, solar hot water system and solar photovoltaic system, all these things will have additional points of 10 each. That is total you can get 20 additional points to demonstrate compliance. So for example, if you will say, okay, cannot meet any of the minimum requirement under say interior exterior lighting or elevators or pumps or something, and still you need to show minimum compliance, there these additional points by installing solar hot water system and solar photovoltaic system will be handy to us. In order to demonstrate compliance with code using point system method, the ENS building must obtain the applicable minimum points as specified under section 6.1 and get remaining points by meeting requirement label as additional points of building envelope under section 6.4 and or meeting the requirements label as additional of building services and indoor electric end use under section 6.5 and 6.6 and or meeting the requirement labeled under additional or renewable energy systems under 6.7. So the mandatory points or additional points shall be assigned as per the least energy efficient specification of all products installed under a category in the building, unless the trade-off or weighted average is allowed for a particular category by the local. In a mixed mode building category, the energy efficiency measures applied in the common services and installed at an overall site level shall meet the most stringent specification requirements among the mentioned requirements of different categories of building to claim mandatory and additional points. To claim the points under renewable energy system section, the renewable energy system can be installed collectively at site level or installed collectively at one or more roofs as per the total renewable energy installation requirement for the entire project. It might be possible that in one of the building rooftop you will have a clubhouse or you will have some other requirement, but the other couple of buildings you will install your solar roof totally in a say a housing complex of 4 or 5 buildings, so that is perfectly acceptable and allowed. So for building envelope, as I mentioned, you have 47 points minimum. Additionally, you have 40 points, and so maximum you can achieve 87 points. Then for common area and exterior lighting, you have 3 and 6 points. Then for elevator, it was same as 6 and 8 points. Electrical system 1 and 5 points additional for submitting and other things. Then for indoor use, you have this thing. So this table again is showing you a total ENS score where comfort systems are also included. Now we come to a main part of our demonstration of energy compliance or HVAC component or thermal component part of ENS. All other areas are there and currently as because it will take probably more than a whole day to cover ENS requirements as a whole. So here we are shifting our gears and coming to our thermal comfort provisions for under ENS first. ECBC we will deal it separately and it will go hand in hand along with other HVAC concepts and requirements. So the score breakup for comfort system for ceiling fans and air conditioning is mentioned in table 20 and table 21 of ENS. If comfort system is applicable in such case, minimum marks for ceiling fans and air conditioning have to be met, and that is mandatory. So for ceiling fans, points for ceiling fans will be only applicable and could be achieved if all the bedrooms and hall in all the dwelling units are having ceiling fans, and point could be gained if installed the ceiling fan efficiencies as per table 20. Similarly, for air conditioners, point can only be applicable and achieved if all bedrooms in all the dwelling units having air conditioners, either unitary split, VRF or centralized plant, and points could be gained if installed as per specifications mentioned in table 21. And in case of air conditioner installed are of mixed type, in that case calculation of point will be based on the formula. So for ceiling fans, minimum if opted, so all ceiling fans installed in all bedrooms and hall in the all dwelling units shall have a service value as for sweep size of less than 1200 mm or equal to greater than 4 meter cube per minute watt, you will get 6 point. Or if we have a sweep size of more than 1200 mm or equal to greater than 5 meter cube per minute watt of fan capacity, you will also get six points for that. BEE standards and labeling requirement for ceiling fan shall take precedence over the current minimum requirement as and when it is notified as mandatory. So like I mentioned about the refrigerators and air conditioners and other equipment or appliances standards, the BEE, if they upgrade these ceiling fan requirements, then we will have this thing. So minimum value requirement of these 4 meter cube per minute watt or something, that value will change and will get lowered. Additionally, if all the ceiling fans installed by in all bedrooms and hall in the dwelling unit are either 4-star, then you will get 1 additional point. And if they are all fans are 5-star, then you will get 3 points. So meeting minimum efficiency is mandatory, as well as additionally you can get 1 to 3 points. And places like Kerala, where ceiling fans probably be running all the time, then investing into a 5-star system will always be a wise choice. Similarly, for thermal comfort, our minimum efficiency if opted, so unitary type 5-star split AC unit, 3-star VRF will have a COP of 3.28 ER. And for chiller, minimum ECBC level values as mentioned in ECBC 2017. So you will get 20 points. If split AC is 4-star and currently VRF, there is no star level this thing program, it gets launched, then 4-star under VRF also will be applicable. And chiller minimum efficiency will be ECBC plus level. As mentioned in ECBC 2017, you will get additional 9 points. And if we install all our split ACs are 5-star, VRF again, when the labeling, BEE labeling would be applicable, a 5-star label should be installed, and chiller again, super ECBC level values will be installed. So then you will get additional 21 points. So if for demonstrating compliance, without air conditioning, you use ceiling fans which are efficient and BEE star rated 4 or 5-star label, and you will achieve it. It will also reduce your bill substantially. Like I mentioned, in an average, if any ceiling fan is used probably for 10 or 12 hours a day, then you will start saving more than 1 unit per ceiling fan per room. And overall, you might save about 50 to 60 units very easily per month, which at a value of say 10 rupees a unit, you will probably be incremental cost. So ceiling fan usage for more than 10 or 12 hours, it always makes sense to go for 5-star label ceiling fans. Even as a developer, if somebody wish to give that as a part of amenity, they should also give them as a part of amenity in terms of 5-star label fans, because then that incremental cost will always pay back very easily. So we have one question over here. What is stilt? Yeah, stilt is covered area at the ground floor level. So where you don't have offices or flats or something, so you use that area for shaded parking. So that is called stilt. So it's only columns are there and height is less or good enough to park your two-wheelers and four-wheelers at the ground level. So in case there is not enough area available for open parking, like in case of Mumbai or something, so either buildings have stilt or there are podiums built, because parking all vehicles on the road itself is not possible in larger cities. Again, same case in Thiruvananthapuram and Ernakulam areas. So you construct or don't build a flat or office or anything on the ground level, and provide shaded parking for your vehicles. So that is stilt. Yeah. Anything else you would like to know? What about tower ACs? Tower ACs again are part of split AC units. Only they are built differently. Or even bigger size units will be coming under purview of package units. So again, for package units, you will have to refer to ECBC 2017 values. So even for a residential area, see, if you have a tower unit of say 2 TR, it acts like a split unit only. But if you have a tower unit of 5.5 TR, 7.5 TR or bigger capacity, then they go as a part of package units, and then you will have to refer to your ECBC rating for their COP values, because then those larger units are not covered under star label program of BEE, and then they are covered under ECBC. Is it clear? Any doubts, anything on ENS requirements? Any questions? Hello.
Am I audible?
Yeah.
Sir, these points 47, 70 and 100. But what is additional points? This 47 is for envelope, you will get 47. So along with additional point together, we should get 47 for rating. Is it like that?
Yeah. So like here, if I show you this, right, you can see this table. So if you meet certain other requirements, so this is, we are not here dealing entirely on all aspects of ENS. This is, we are just touching ENS as an introduction, as well as looking at only thermal comfort requirement of ENS. See, because like ECBC, ENS also has your envelope requirements, then you have elevators, pump, electrical system, lighting, comfort system, everything. So for every other aspect, like in building envelope, how you are dealing, if you are dealing with only minimum requirement of U value or RETV of below 15, then you will get certain point. If your RETV is say 20% better than 15 watt per meter square, then you will get certain additional points like this. So means when probably already there must have been a session, or if it is going to be held by Kerala EMC in the future about only pertaining to building ENS, because that itself will run through the day. And here we are today discussing only thermal comfort and air conditioning requirement. So again, when we will be touching ECBC, we will not be touching of electrical requirements or the envelope requirements or something. Envelope we will keep on touching, because envelope becomes major part of our heat gain. So having a better envelope also helps you in, as I mentioned, in reducing your building size or a building cooling requirement. But if you don't means, so if we look at all other aspects of ECBC, I'm sure, yes, in the past also, in fact, I have conducted many programs for Kerala EMC for entire ECBC, and all aspects of ECBC 1, 2 and 3 days program have been already done. and if there could be some recordings or something could be available from the past itself, so you can check up that. But each and every aspect of ENS or ECBC cannot be covered in a day. So here today we are talking about ENS and maybe requirement of ECBC we talked, but then there is huge lot of requirement coming under HVAC itself, which is today's topic. Yes, if there is a time or there is some other program, if we launch, then yes, we can touch upon envelope and lighting or other services as well. But air conditioning in ECBC is huge, and everything has a requirement and basis. So I expect when we then turn to ECBC requirements or something, then we will have more interactions or questions coming from you rather than just me running through the slides. Yes, we will do that, but then if you have any doubts or question, you can ask. But for pumps, electrical systems, elevator, lighting, for every meeting and meeting those requirements, you have this thing. And this ENS code, ENS2, CNN2 is also available in public domain, and that can be referred as well for more details. Or else whenever probably we will have a separate program by Kerala EMC on those aspects, it can be taken care of. Yeah. So any other doubts, sir? I think while calculation of COP in denominator side, we shall take compressor electrical input alone, or we should take full electrical input including pumps. No, when we will deal with ECBC, we will address this. But when we talk about COP of a chiller, it will be only compressor power. When we talk about efficiency of entire plant room level system, then it will call for compressor power, primary chilled water pump power, secondary chilled water pump power, and your cooling tower fan power and cooling water pump power. If it is a water cooled system, if it is an air cooled system, then it will have compressor power as well as your air cooled fan exhaust fan power. So all these will be covered as a part of plant room efficiency. In air cooled machine, cooling tower will not be there, but fan will be there. Primary pumps will also be there in both air cooled as well as water cooled system. Yeah. What about kilowatt per TR and IPLV in above cases? Yeah. So kilowatt per TR and IPLV, we will come to that when we will discuss about ECBC in detail during the day. So, and for every type of building, ECBC plus and super ECBC, we have different values and more stringent values coming. But again, as I mentioned, to look at air conditioning, I need to look at design first. Because unless I make my envelope very efficient, I will keep losing energy to the surrounding or atmosphere easily. See, understand one thing, air conditioning has come to us from the Western countries, Europe or North America, where predominantly more than 8 months in a year, there is a biting cold, which human cannot sustain. So their style of construction has been evolved to construct sealed buildings. Their windows will be shut tight, or they have requirements of adding sealants, putties, everything above the windows and door frames and everything. When we started constructing these glass box buildings, see, if you construct a glass box building in Europe or North America, it allows a lot of sunlight to come inside and it reduces your building heating load on gas or electricity. But in our case, it adds to heat load. See, so rooftop. So skylight, yes, we are all fancied by having a skylight, but skylight, how much heat it brings inside? I will give you an example of one small commercial mall in Delhi. Their normal cooling requirement of that very small mall, the three or four-story mall with some small multiplex theaters, a couple of shops, and then on the top there is a small food court. All that, not a very big mall, but there they operate typically 150 to 200 ton as their base cooling load, including all shops and all these areas which I mentioned through this centralized system they have. And in the center, they have about 60 feet or maybe 20-meter diameter of a atrium in Delhi. And on the roof or the top of the atrium is just a polycarbonate sheet of 8 mm thick. For that heat gain through the building in summer months, that is for more than 6 months in a year, they need to run one more 150 tons of air conditioning system. If you compare their monthly electricity bills, this difference is evident. Even it reflects. So their summer air conditioning bill goes up by 50% straight away. And in winter also, they run at least one AC unit and maybe 2 units as a adjustment in the cusp months of beginning of winter and beginning of summer. But in summer months, straight away one additional chiller operates. That is the amount of heat gain which is coming through envelope. So now only chance is, but the design is with the central atrium. Yes, it adds to beauty of that building. Answer is yes. But then at what cost? The owner wants to change that now, and that is where we have been discussing with them. So if you see these requirements, so COP, kilowatt per TR, everything is fine. We understand that. But then how much load it gets added to the system is also important. So in ECBC, skylight has been capped at maximum 5% of the roof. In any climate other than cold climate, which allows or requires heat to come inside the building, but all other four climatic zones, that is warm and humid, hot and dry, composite and temperate climate, our minimum skylight applicable by ECBC is just 5% in a prescriptive manner. We don't need that so much amount of energy or heat to come inside. So this is important. Then adding shading device to the building, then it plays a role. So all these requirements have to be looked at in one or the other way before we conclude our design and release our drawings or float specifications and close it. No, we need to look at all these aspects at the design. So making design envelope better will help you in reducing your HVAC, which I showed you an example. By making building envelope better, our air conditioning load for that project came down by 28%, which is substantial. I'll show you a couple of other case studies as well, so how to look at all these components. But then while we discuss about air conditioning, we will always keep going back to your envelope design, orientation and other aspects. So kilowatt per TR and IPLV, yes, they are good for selection. But again, if they are used without controls, we will probably, they will not be still effective. See, I can always install a VFD screw chiller in a system for a building. But for that VFD to function, if I don't put a secondary pump on VFD, if I don't put two-way control wall and allow them to modulate and allow my AHU fan, how this goes? So my air conditioning system is, I need to supply say typically 7-degree chilled water at my chiller outlet to the room AHU. So the room air, return air will come at about 65-70% relative humidity at 24-degree, 25-degree centigrade. That will be my room temperature. So part of that air will come, it will get mixed at the coil, get it cooled, dehumidify, it will lose that humidity, and then dehumidified cool air at 14 degree and 98% RH will be sent back to the room, where it will pick up again heat and humidity. So the amount of AHU or fan capacity will be typically 15-20% of the total fan requirement or the air movement requirement of that room or section, and it will keep happening all the time. So at the grill of every room, the temperature would be 14 degrees at 95-98% RH. So that air will get mixed with 24-degree air. So that addition of cool air will be equal to your heat removed or heat gain by the envelope as well as people and systems like computer, lighting, etc. If any of these mismatches, if my ambient temperature keeps increasing all the time, then I need to increase my air conditioning. Otherwise, people will be uncomfortable in spite of air conditioning. Second way, if my inside conditions get my energy requirement goes down, then my cooling requirement also has to go down. Either my AHU fan speed has to go down, then if in auto mode my two-way or three-way control wall has to go down, and if my two-way control wall is operating, then a VFD on my secondary chilled water system has to go down, and it should give a signal to chiller VFD, and chiller VFD compressor power also has to go down. Then my system will be efficient. If any of these things doesn't happen, then I have an indirect or inefficient system, even though it has been selected for better IPLV or better kilowatt per TR value. I'll give you an example which all of us have experienced pre-COVID era in a multiplex. If we go in a theater, so in a multiplex, mostly they supply cool air at fixed speed. There are no VFDs or something. So for a thermal comfort, if our metabolic rate when we are sitting and just watching a movie or enjoying a movie and not doing any movement, something, then our metabolic heat requirement also goes down. And after a while, we start feeling cold. And if there is an interval in the movie, we welcome that and just we go out, stretch our legs, have something, food or something, and then we come back. But otherwise, if there is no interval or something, then maybe many of us feel uncomfortable. That is because there is a buildup of humidity as well as lower temperature, and fan speed is fixed. That is also, it has a commercial angle, so that you will go out and eat some food or have some hot tea or coffee. So there will be a business for the food counter outside. But for person's thermal comfort, no control on the fan speed, because my metabolic rate, see, when we come from outside hot environment inside the mall or inside a multiplex or something, then yes, we need probably that kind of extra cooling required. So for initially half an hour, we will feel better. But once our actions have become sedentary or close to nil, then yes, then we will start feeling shivering. Also, if there is not enough chilled water temperature, then increase humidity in the return air of more than 70% will also make us shiver more. So shivering will happen because of lower temperature, as well as additional humidity will also play a major role. So all this comes as a part of thermal comfort or thermal discomfort. So alone selection of one equipment, that is chiller, based on a very good IPLV or kilowatt per TR does not mean anything. See, because same AC, and I will give you an example. See, because Kerala mostly we have, or in coastal areas like Mumbai, we have almost stagnant or similar climate throughout the year. Only few variations are there. Yes, but otherwise our main humidity and temperatures, they don't vary large. But in case of places like Pune, Hyderabad, Delhi, composite climate, where they have harsh summer, low humidity in summer, and very severe winters as well. So all those central part of India, or maybe more than 50% part of India, where they do require to have controls on the system. I remember a factory in Bangalore which was producing some electronic components. So that entire assembly also needed to be air conditioned. Outside condition during that visit in month of November, it was very cool, and outside ambient temperature was 14 degrees centigrade. It was partially raining or almost this thing. But even inside that building, to maintain temperature of 25 degree, two numbers 200 TR chillers were operating. Because in that building, there was no provision to take outside cool air, filter it, dehumidify it, and spread it in this thing. So otherwise, same 14-degree air coming either naturally or coming out of your AHU will have the same impact. But unfortunately, they didn't had that system where they could just take pressure from outside, filter it so that there is no dust and other particles are going inside, and just run through the duct in one go. Your entire 400 TR of cooling load on the production area could have been stopped. And in Bangalore, there could be probably more than 2000 hours in a year. Very easily, this kind of condition can happen. In Pune, such hours are almost like 15 or 1800 hours in a year. Delhi is similar or little more. So that means if you have these kind of systems design, your cooling load can come down. Unfortunately, yes, in places like Mumbai or Thiruvananthapuram, Ernakulam, we don't have this kind of liberty for longer. So even BEE code also says for warm and humid climate, they don't allow us to ask for free cooling or any alternative cooling technology, because otherwise cost of that will be higher. Means you won't get payback for designing those systems. But in central Indian plateau places, yes, these systems can reduce your air conditioning load significantly and for significant amount of time. And if you are talking about hospitals or any such 24/7 operational data centers or call centers, etc., then that savings then become huge. So looking at these things, we will have now move over to the next level. So no questions right now on this. So HVAC system or air conditioning system is all about thermal comfort. And how do we provide this thermal comfort to people or a group of people sitting in their respective area of work or homes or wherever? In a scientific journal, the definition of thermal comfort is a state of mind that expresses satisfaction with the thermal surroundings. This is a definition of thermal comfort in a scientific journal, but talks about one component, that state of mind that expresses satisfaction. So can anyone of this group tell me where the mind lies within our body? Yes, if we ask, yes, heart can be at least said, yes, there is a heart, there are lungs, there is nose, tongue, teeth, all those elements or body parts, brain, which can be scanned and seen. All these are possible, but then where is mind? There is nothing in physiology books like mind. But psychology also only talks about mind, mind, mind. Where is that? So mind is probably agglomeration of all five senses that our body can experience, and then that is that state of mind that would express satisfaction with the thermal surrounding of the building. The human body needs to be maintained at 36 plus or minus 0.5 degrees centigrade regardless of prevailing ambient conditions. Even either we are in tundra or at the North Pole or South Pole, or we are in the desert of Rajasthan or Kalahari or Sahara of Africa, our body temperature will be 36 plus minus 0.5% always. So in very cold climate, we will consume much more energy. So in North Pole and South Pole, we will have to eat 10,000 calories of worth of food to keep our body warm. Otherwise, we will start shivering because our ambient body will, in spite of layers of clothing, we will lose that energy to surrounding. In the hot climate, we will have to manage with lot of liquid diet as well as lower food intake of 3,000 to 4,000 calories, and to meet our metabolic heat requirement and maintain our body fluids. Air movement is essential for comfort as it enhances heat transfer between air and human body and accelerates cooling of human body. All of you are listening to this session, and here I am talking with you continuously. Now I am feeling probably a little more exhausted or this thing, because I am consuming more energy than yours relatively. In spite of if we are sitting in the same atmosphere or air conditioning room or room served by ceiling fan or whatever, but our consumption of energy, mine is on little on higher side with respect to yours. But at the same time, if Usain Bolt is running 100 meters of his sprint race somewhere outside, then he will need much more energy, as well as he will need much more air movement to give him that thermal comfort after he finishes his 100-meter in less than 10 seconds. So you feel comfortable when metabolic heat is dissipated at the same rate it is produced. So for Usain Bolt, if he produces much more energy, so his food intake, protein intake will be higher before the race, and after the race that entire heat has to be dissipated quicker. But for us sitting in a lecture or discussing, sitting in this thing, so our calorie intake will be low, our heat this thing will also be the cooling requirement also could be lower, and we can be probably comfortable with some ceiling fan running around or something, so that there we are not sweating. So that air movement gives us a feeling of freshness by lowering skin temperature, and then the more varied the air currents in velocity and direction, the better we feel. A draft created when temperature of moving air is too low or velocity is too high. If we want to decode that concept of thermal comfort into a more technical numbers, then comfort of room temperature for office work or learning or sitting and working will be 23 to 26 degrees centigrade, and acceptable air velocity range will be 0.15 to 0.5 meter per second. And the higher the space relative humidity, the lower the amount of heat human body will be able to transfer by means of perspiration or evaporation. So this was I was discussing about that multiplex. So they don't they increase either chilled water temperature, or they don't add fresh air or exhaust some of the stale air, and they keep circulating same air. So the moisture in the conditioned air or inside that multiplex goes up very high, and lower temperature and higher relative humidity will make us shiver. If the indoor air temperature is high and RH is high, which will be again 11.5 gram of water vapor per kg of dry air, human body will feel uncomfortable. So this is, we are talking about moving in the sun in Kerala or in Mumbai and in the summer month. So where we will have more than 35-36 degree temperature. So there is no temperature difference between inside and outside, or body temperature of 36 and ambient condition of also 35-36, as well as outside humidity is more than 70 or 80%. So if on a psychrometric chart, if this 11.5 gram of water vapor per kg of dry air value goes up, then we start feeling uncomfortable. Then we need to quench our thirst by having water or something. And generally for any indoor application, more than 70% RH, if it is not exceeding, then people will be comfortable. So in many hospitals or even areas, non-critical or critical areas, you need a controlled environment. But in many areas, even I'm just giving an example here of a area of critical nature like hospital, where okay, OTs and ICUs, you need to maintain and control temperature, RH, everything. But your maybe normal patient bed areas, normal examination areas, waiting halls and everything, you don't need air conditioned spaces all the time. You need a comfortable temperature and low RH to be maintained. So by doing this, you can reduce your. So this is a typical psychrometric chart. And if you can see my cursor moving, when the temperature is in the range of 15 to 20 degree, this is my dry bulb temperature, and these curved lines which are originating from the left bottom corner and going to the top right corner are the relative humidity lines. So the outermost line is the 100% saturation line, and the horizontal lines here, whatever you are seeing, are the these are the vapor lines, which is, as I mentioned, 11.5 grams of vapor per kg of dry air. So that number of absolute humidity is displayed over here. This is not relative humidity, but absolute humidity, AH. And these lines are of relative humidity, which are curved lines. So if you have anything which is up to 70% RH and any dry bulb temperature varying between 15 to 20 degrees centigrade, it will be a cool climate. Then this is a moderate climate when you have a temperature of 20 to 26 degrees centigrade, and again relative humidity not going more than 70%. You will be still comfortable. Then it comes as a hot and dry climate where your requirement of this thing temperature would be 27 degrees to about 34 degrees or 33 degrees, and relative humidity will be much lower in this range, which will be about 50% or below, even going as low as 30% or 20%. Then you have a hot and dry zone, which is part of Rajasthan or areas of Gujarat or something, where you will have temperature ranging between 33 to 44, 45 degree, and the relative humidity will be 10% to about 40% or 30%. So you will need to add humidity to the air to cool it down, as well as people staying there need to drink a lot of fluids or water to maintain them hydrated, because otherwise that outside heat itself will dehydrate your skin and body. Then on the top you have two zones, warm and humid and hot and humid. So Kerala falls into these top two zones where you have warm and humid climate, where the temperature is not very high, or part of year you experience temperature of 26 to 32, which is less than body temperature, but humidity of 80% and 60%. So you will still perspire and sweat around. And then comes the worst part, monsoon month or just beginning of monsoon or something, where you will have temperatures of about 38, 40 degrees. See, predominantly Kolkata and Chennai falls into this hot and humid climate, not just warm and humid climate, but hot and humid climate, where ambient temperature also are around 40 degrees in summer there, as well as humidities are very high. So absolute humidity, if you measure in both these cases, which is always above the comfort zone. So you will continue to have more humidity removal load on your air conditioning system, which is enthalpy gain, which is one of the major component of your heat load or air conditioning requirement. So what is the major or the strategies for maintaining our body temperature comfortable by using any of the techniques? So passive design is the thermal mass, So massing is one of the effective passive strategies to increase thermal comfort inside the building. The purpose of massing is to provide thermal barrier to heat transfer inside the living spaces. And in the modern scenario, it is not possible to construct thick walls, as it would cost of cost of construction as well as the available space it would eat into. See, olden earthen houses or stone houses used to have 2 feet thick walls. They were essential as well because most of the times a lot of wars and other conflicts were going on. So for protection against physical this thing, any damage also, the house would be built like a fortress. But in today's condition, we don't need that. But then we can do or achieve similar effect only to hold the thermal comfort by adding insulating materials with better thermal properties than our normal brick or something. So I'll show you and tell you an example. In Mumbai, there is a concept of shear wall or Maiwan construction. So when we have high-rise buildings, residential or buildings done mainly, which are more than 40, 50, 60 floors in height, you need to complete that project fast in time, as well as you don't want that those flat owners to complain about leakages or something through the walls or gaps between columns and something. So the entire outer wall or envelope is built like an RCC or Maiwan or shear wall construction, where in the walls and columns everywhere you add concrete and metal this thing rods or steel and fill the concrete and complete. So you get an uniform shear wall without any leaks or something. So having issue of water ingress is avoided, and now you can maintain that building fast, construct faster, because in my 3 or 4 floors can be constructed much faster, and it can be done. But then when you talk about heat gain, because concrete is a material which is conductive, inside that there is a conducting material of iron or steel, which also heats up the thing. And once all these members of steel are tied together in terms of tie rods and other things, so all columns and beams, everybody, they are interconnected, they become or called something called thermal bridging of the envelope. So during daytime it heats up so high that it will be impossible for anybody to sleep in that room which has gained heat from south or west side walls without air conditioner. So to kill one demon of water seepage through the outer walls, developers have used this building, and then to kill that, they also then provide air conditioner as a part of amenity to the flat owners. But then poor flat owners, they have to pay for those monthly energy bill. Otherwise, without that, they cannot survive in those houses. So the thermal comfort kills them. So yes, water seepage issue is averted, but then the solution chosen is not the right one. And this is how practically most of the buildings in cities like Delhi, Mumbai, Bangalore are built today. Unfortunate part of it, and none of these buildings qualify for ECBCR or Econivas Samhita prescriptive requirements as well. So they cannot ever achieve RETV of 15 or below, 15 watt per meter square or below, because of inherent higher thermal mass, this thing, or energy gained by that structure. So thermal mass should be good enough only to create a lag or delay for heat transfer. There is another example I will give you of buildings built during British Raj in Delhi. All these North Block, South Block, and other lot of colonial buildings, they have been built with very high thermal mass. So what happens? This high thermal mass during longer summer days or months, they get exposed to solar energy and they retain that heat so much inside their thick mass that even during night hours those buildings remain warm, and then sky radiation is not good enough. So once the next day again person comes into that building is still not fit for sitting there and working, so they need to go to air conditioners in the summer months, because in summer months days are longer, nights are shorter, in which are more predominant and pronounced in the northern part of India. And in winter months, your day is shorter, nights are longer. So whatever cooling, even this year they were recording a temperature of daytime temperature of 7 or 4 degrees as well in Delhi. So that part of time, that entire thermal mass is cooled so much that people inside start losing their body heat to the surrounding very fast and they shiver. So they need to put on room heaters because central heating is probably not have that we don't have in most part of the buildings in India. So because of very high thermal mass or excessive thermal mass, these buildings are non-livable buildings throughout the year. Either you need heating or you need internal cooling to make people thermally comfortable. So even excess mass with respect to climate is also not good. And then selection of materials also plays a role in that. So it should just create a lag or delay so that by the time sun changes its direction, the heat gain by the surface will be gone. So typically in Kerala, we get about 350 watt per meter square of solar insolation, direct solar insolation on any of the surface, be it roof or wall. In wall means east side wall will receive it on morning hour, south side wall will receive probably major part of the day, and west side will receive in the afternoon after 3:34. And at the same time, sky radiation happening will be only 50 watt per meter square. So for 6 hours of solar ingress, we will continue to have our ingress of 350 watt having incident in the first hour, and at the same time sky radiation is going at 50 watt per meter square. So per meter square per hour, our net would be about say 300 watt in the first hour, but 300 we have retained. So in the second hour, we will add another 350 watt and lose only this thing. So 650 will be your total heat gain and 100 would be outing. So every hour through the day, we will keep on getting that solar ingress. So building will become warm. And in the night, sky radiation, there will be no sun radiation. So after sunset, entire radiation will go to sky. But if sky is cloudy, then that radiation also will not be more pronounced. So on a clear sky, the cooling will be more effective for sky radiation. But on a cloudy day, that heat may not go or travel to the sky, which is at sub-zero temperature even during daytime. So all these things we need to understand how that heat transfer would happen, and then what is that adequate number. Again, not to calculate it by everybody, ECBC in form of a code has given us these prescriptive values which we can meet by selection of appropriate material. So this is where a wall insulation will help. So the red line is wall without insulation and the blue line is wall with insulation. So if we have no insulation, our cooling demand in these are months 1 to 12. So in winter months, our cooling demand would be this thing. But then without insulation, our heat gain during summer months will go up or it goes up. This is a simulation output, just comparing. And then with insulation in winter months also, we will probably require some energy. Here it is almost zero for 3 or 4 months, but here we will still have. But our peak heat gain during summer months is much lower, and that compensates for insulation. So we don't want to do so. Building with insulation will always have some energy requirement even during winter months with appropriate insulation, but my peak summer cooling demand goes down significantly. So this is an impact of my wall insulation on the material. Again, like we have wall assembly with light shelf. So light shelf will allow, or it is a panel here which will allow my daylight to penetrate and wash my ceiling. So there is enough reflected light coming without heat. So the light shelf provide resistance to heat gain. So here you can see these fins or the external area itself is getting some this thing direct sunlight, but all my windows are protected from heat gain. So heat gain by these window materials are then less. So then my vertical fins as well as horizontal line, it is allowing daylight to come inside, but not heat. So that is where uh, this is a combination of having lighting and air conditioning. This thing, your thermal comfort, not air conditioning, I would say thermal comfort to be clubbed together. Other aspect is to have external movable shading devices. So not to have these Venetian blind kind of blinds inside the building or inside the room, but provide them on the outer surface. If we simulate this, if this is my wall, so this is my solar gain, and through my window assembly, it is coming. So because of reflective properties, some amount of heat is reflected, and this is my indoor blind. So some amount of heat also penetrates and gets trapped between my blind and the glass, and some amount of again is reflected by the blind, but it still remains trapped inside. And that even though I am using a SHGC or solar heat gain coefficient factor of 25%, but because there is a direct incident light or heat on that, my effective SHGC becomes around 40% or more when I put my blinds interior. But when I put my exterior blinds, so I have same glass assembly, I have same sun, but I have now blinds outside my glass. So entire heat dissipation happens outside itself, and very less heat goes inside, and my effective SHGC is less than 10%. So instead of going for a double glaze unit or a DGU, which will cost me about 400 rupees a square feet, I can go with 60 rupees a square feet single glazing and have external movable shading or something, which I can use only when my sun is directly approaching through that window. And I can reduce my effective SHGC and also reduce my peak cooling load requirement for the building. Impact of having a west orientation overhang. Here you can see on the top there are two cases. One, this is my this blue line here, this is my west side wall, and this is my glass which has been simulated, and this is we have put an overhang. And the second image is overhang with external shading. So here monthly peak gain shown by the red line is more than 120 or 130 watt per meter square is the heat gain probably throughout the summer months here. But if I put an external shading device, my peak energy watt per meter square is always less than 40. So I save almost 2/3 of energy coming through my air conditioning system by better envelope design. See, so with simulation, you can impact or study impact of all such design aspects. This is another building done, which is a college building. So they have a lot of these trees outside, and also they have created a double screen facade. And the material used is just a Shera board, which is a cementitious material board, which is very good to be installed, a cheap material which provides natural screening to the window behind. Also, the trees are shading. So this is a college campus. So for a G+3 structure, these kind of cheaper solutions of double screen facades, etc., would work better as well as reduce the heat gain. And the wall is of course constructed in the stone, so which is also good. But then open grid pavers, they will also reflect very less energy. Then creating microclimate is another such area. There is something as a concept when I was showing you this thing. The solar radiation come to us via shortwave radiation, and once it hits some surface, glass, wall, or any roof or something, then that shortwave energy gets converted into a long wave energy, and then long wave radiation does not have ability to travel longer distances. So that heat will remain just around your building or in the nearby area, and then that collectively is called heat island effect for the building or group of buildings. So what is that heat island effect? If you read this terminology in building physics, so your entire solar radiation which comes into short wave, if you can reflect that again back at the short wave itself by using high reflective index paints or coatings, then that energy would travel further. But if it hits any normal surface, then that short wave radiation would get converted into a long wave radiation, and then that long wave radiation would remain just outside your building envelope and would eventually heat up the building envelope. So by using cool roofs or highly reflective walls or materials, you can avoid that heat island effect as well. And then creating again these kind of natural green surfaces, adding that, because again all these stones you are seeing, these slabs or the tiling will also gain the heat and start radiating that. So bare feet you can't walk on that, but during daytime you can very easily barefoot walk on this grass any time of the day. And in fact in the early morning, the dew, because of dew, it will be very cold as well, because that entire moisture in the air has condensed over those grass blades. But walking them on the summer afternoon is almost next to impossible. So creating these kind of microclimate in open spaces around the building is also good part of design. So when we talk about this air conditioning system, what is my objective of HVAC system? When we do this and we talk about efficient system, or somebody was asking, Anish was asking about kilowatt per TR or what is IKW, IPLV values, etc. What is the purpose? It has to remove sensible heat from a conditioned space to maintain constant temperature inside it. It has to remove water vapor or a latent heat from the conditioned space because of to maintain constant and acceptable humidity inside. Remove dust generated and contaminants in a confined space by air sweeping it. Prevent dust and atmospheric contaminants from entering a confined space, and prevent microbial growth and cross contamination between these spaces. So last three parameters, dust removal, atmospheric contamination entering into consideration, and microbial growth and cross contamination. COVID has taught us really well about all these requirements. To have a filtration unit of HEPA filters or MARV13 or better filtration in confined space, nobody was talking about it. Only in hospital OTs they were done. But now when you have just not window split AC units are enough, but to provide a good level of filtration is also essential along with that. One of the learning from COVID is also that you can't keep on circulating same air inside those areas. You need to refresh that with the fresh air or have continuously fresh air going to those areas, and contamination or the concentration of bacteria, virus, anything which should be kept aside should be maintained low. So parameters an HVAC system inside a conditioned space would maintain would be temperature, humidity, pressure, particulate count or dust loading, that is PM 2.5 T, PM 10, and volatile organic compounds, VOCs, and the CO2 level. By maintaining adequate amount of fresh air coming to the room, your CO2 levels should be maintained. Particulate matter, by applying a good level of air filtration at the AHUs, you will maintain the dust loading. Temperature, you will maintain anything between 23 to 26. Humidity also will be always, you will maintain it between 45 to 55 or 55 to 60% RH. Pressure will be good enough, not just little more than atmospheric pressure, so that no infiltration of system will happen, but it can only do a exfiltration through the system. and volatile organic compounds generated from our computer screens or printers or any such other, even cooking in the hotels or other areas can generate organic fumes, which need to be controlled, because otherwise they will start adding to your this thing, contamination of or mold or algae, fungal growth in the rooms, etc. And what an AHU can manage? AHU can manage only temperature, and temperature, nothing else. AHU coil has only one control. Most commonly, it is a return air temperature to bypass the chilled water flow to the coil. And humidity control is additional load. It can be managed by adding a sensible heat to supply air through reheat or something. So humidity control in most AHUs where it is required to be maintained, like OTs or ICUs or any pharmaceutical manufacturing areas, where humidity control, for that they will have separate hot water coil or a steam coil or some coil is given, or even electrical coil is given to maintain humidity for reheating that air. So the air which is going to those areas, critical areas, is always controlled in terms of both temperature and humidity. But otherwise, all our comfort air conditioning system manages only temperature, and temperature. Pressure control through pressure addition and exhaust purging is also it would do, and indoor air quality control through filtration, UV lamps, etc. It will also monitor and manage, provided you have designed for it. So higher level of filtration. See, most of these things in commercial offices during COVID time, everybody started aware about something called, which is HEPA filter. So till that time, HEPA filters were used only in the OTs and ICUs. But now, to avoid COVID virus to be arrested, people started talking about HEPA filters or MERV13 filters, pre-filter, etc. Most of the office AHUs installed and in last 10 years or more don't have space also, because a HEPA filter will have a filter width of more than 1.5 feet, 450 mm or 400 mm of filtration depth itself. And our normal filter will have a depth of what? Less than a few millimeters. So even a 10 micron filter will have a depth of less than 15 mm or 20 mm at the most, including frame. So that is not enough to take. And also, so for upgrading all these existing AHUs by these HEPA filter or MERV13 or better filter after COVID is almost impossible, because either there is not enough space in the AHU to add this section, or there is also no room in the AHU rooms provided to add these kind of sections in front of AHU. Because to have additional 2 feet of space, most of the AHUs have never been designed accordingly. And then we also have fancy systems like ceiling suspended units or something, which can never take care of your higher filtration load, because fan static also needs to be changed. Fan static is the pressure it can overcome by the resistance of filtration. So when you run a HEPA filter, the pressure drop across that HEPA filter itself is 40 mm or 35 mm of static pressure, whereas a normal 10 micron filter will have a pressure drop of about 5 to 7 millimeter of water column. So to change filter, even suppose you have a space of 2 feet to be added to the existing AHU room, you will also have to change your fan. So fan need to be of 60-75 mm static minimum to overcome the pressure drop across coil, filter, everything, and still able to provide that space. So to do these kind of systems, you need to design your AHU beforehand. So this is a typical room side cooling circuit or unit. This is my conditioned space, which I need to maintain at 24 degrees and 50% RH, which is including my sensible and latent load. This is my air handling unit, where I am getting supply water at 7 degree chilled water and return water coming is at 12 degree. So I have a coil. So I am supplying this air from AHU, which is filtered, dehumidified, cooled, to 12 degrees and 98% or 95% RH, which picks up latent and sensible heat from the room, and my return air will be always at 24 degrees centigrade at around 50-55% RH. Then there will be a fresh air load. So in spaces like Mumbai or Kerala, we will have ambient air coming roughly around 35 degrees centigrade and 75% RH for most of the part of the year. So here, by circulating this chilled water in the AHU, we will remove my humidity as well as cool all these air and keep my conditioned space comfortable or thermally comfortable. So this is a job what a typical cooling system would do for maintaining the conditions. Yeah, we have two questions. One is from Saju Joseph, which talks about effective draft temperature considers air temperature and velocity. Effective temperature considers air temperature and humidity. Is there any index which considers air temperature, velocity, mean radiant temperature and humidity together? So see, for mean radiant temperature, all the parameters within the given confined space need to be constant. So the persons should not move. Air should not move in that room. Hence, either we maintain a draft, but we don't change fan speeds or something. So MRT is more of a theoretical exercise. So what will be my effective MRT? See, what is purpose of MRT is whether I will be able to maintain my room temperature or not. And humidity and temperature can vary with respect to temperature. So if you refer to NBC 2016, there is a concept called effective indoor operative temperature, which is subject to your outside temperature. So there is a correlation between ambient temperature and inside condition. So in Delhi or Gurgaon, if ambient temperature is at 45 degrees and 35% RH, and then indoor, if you try and maintain 22 or 24 degrees centigrade, a person which will come out of that cool room to the outside ambient will give a thermal shock, and that body may or may not be able to adjust that all the time if somebody is doing in and out continuously. So there is a multiplication factor. So when your ambient temperature is so much, your indoor temperature should be so much. So in the peak summer, your indoor operating temperature also should go up maybe little more than even 26. Still you will be comfortable, provided with air movement. So index, whatever index that you are asking is more of a variable, and MRT is a theoretical exercise of nature mostly to look at the design. So not one multiplication number will give you this. This thing is, there are complex models available. Through simulations, you can run them, do a CFD analysis and arrive at which will be better or something. So that's what I think. Even maintaining 23 to 24 degrees centigrade or 26 degrees centigrade and maintaining RH 50 to 55% and humidity not exceeding 70% in a conditioned space, these are good enough indicators for 99% of our designs of air conditioning system. If I always tell you, okay, maintain only 11.5 grams of water vapor per kg of dry air to be thermally comfortable, then it becomes Greek and Latin for most of the people. So what you get on a thermostat is a measurement of RH and measurement of dry bulb temperature itself, which anybody and everybody can adjust their thermostats and maintain. So for all theoretical purpose, yes, we can always model something and create some kind of index, but then what a common person like us will do with that index? No. So we will have to give them in a palatable manner, which everybody can manage and understand. And even equipment like thermostat can. Yes, you can always have an absolute humidity sensor as well, but then it will give you some number of kg of vapor per kg of dry air. So you need to have additional equipment, instrumentation and calibration, and still people won't be able to control that and understand how to do what to do with that number. Okay, Aisha asked is, in case where a shear wall is inevitable, what is the feasible solution to reduce energy consumption? Unfortunately, for a shear wall construction, from a developer side, there is no control, because inside, if you put an insulation, then that insulation has to be flame proof. You can't use EPS or XPS for indoor, because there might be some open flame or some kind of heat source generation. To avoid that, and then you need to again cover that with gypsum board or any such material, so your cost of project would go up. And secondly, we Indians, we are fond of hanging things on walls, so we would always want to nail something. So if you put a 2-inch or 3-inch glass wool insulation, then you would have to use probably more than 6 inches of nail, which has to go through the shear wall as well as that outer gypsum sheet and things. Otherwise, whatever you want to hang on the wall would fall down immediately. So doing that then becomes individual choices, how to insulate that and how to maintain. But from a developer side, on a outside shear wall, if they can provide an insulation, that is fine. There have been some theoretical exercises or even some practical exercises done outside India currently, where they are sandwiching insulation between the shear wall construction. But in India, so far, we don't have any of such successful this thing. For a couple of projects, even we had tried and seen that. Everybody says it is theoretically possible, but practically it is impossible. How you will ensure that insulation is stuck very well between your this thing RCC frame, and then pouring happens and insulation is very well protected. It is impossible to manage that. So shear wall doesn't this thing. RH and DPT, absolute humidity, which is comfort parameter. For comfort cooling application, RH is a parameter along with dry bulb temperature, but absolute humidity is maintained for technical areas like manufacturing areas or for your ICU or OT, etc., where absolute humidity could be critical, because very low energy also would reflect to biomedical instruments in that area because of static charge generation or something, and they may malfunction. So maintaining not very low humidity as well as not very high humidity for patients. So there absolute humidity is used as a parameter. But for all thermal comfort applications, I think RH is and dry bulb temperature is a good enough indicator. So I think, can we stop here this session and break for lunch and then come back by 2?
Yes, sir.
Yeah. So Reena, you will again we all join with the same link, right?
Yes, sir.
Right.
We
Sir.
all joined at the same time.
Yeah. So by
We
PM
can
will be,
join by 2:15.
yeah, 2:15 should be good enough. Fine. Okay.
Okay.
Thanks.